All right, so yesterday we talked about chemical reactions. Today we're going to look at a specific chemical reaction that I think is important for you guys to understand some of the basics of what I want to talk about to a certain degree. So one of these things is called electrolysis of water. Now yesterday we talked about the 5 signs of a chemical reaction. Bubbles, solid precipitate, heat and light, color change, and what was the 5th one you had to add? Oxidation. Fantastic, okay? So today we're going to talk about how would you know visually that this electrolysis of water is a chemical reaction. So let's talk about it. First of all, electrolysis. In chemistry and in most scientific classes, if you take these big long words and you chop them up into their pieces, it makes it make a lot more sense. You probably have no idea what electrolysis of water is, but when we break it down, it's going to be a lot more understandable. So first of all, let's start with electro. Do me a favor, make sure you write the slash between the O and the L. Okay. What does electro mean? What do you think where that comes from? Very good, electricity. Now, what is electricity on a basic foundation? It's the flow of electrons. Okay, make sure you write that down. AJ. Okay. So electro means electricity, which is nothing more than the flow of electrons. Now, let's go back to your biology days. Let's see how good some of you remember stuff. What does lysis mean? Ooh, that's a good word. I like that. Anybody got anything else? Lysis. What part of the cell does lysis? Come on, people. The lysosome. Ooh. What did the lysosome do? Okay. Lysis means to split, disintegrate. I like that one, Taylor. That was good. So lysis means to split in this term. So the lysosome basically broke down bad things that were in the cell and kind of deteriorated. Remember, like Lysol, right? Lysol is a bacteria killer. This is kind of where the name comes from. So now, if we read it from this perspective, what is the electrolysis of water? Using electricity to do what? Split water. Okay. Now again, electricity is just the flow of electrons. So we're going to shoot electrons into the water and we're going to split it. Now, I'm going to come back to this picture, but I'm going to kind of jump back and forth. So do me a favor. So underneath this slide or wherever you have room, write this. So we're going to take water and we're going to split it. Now again, what are we using to split it? So just do me a favor and write that right there. What do you think that stands for? Electrons. Okay, it stands for electricity in the shorthand. We're going to split it into its parts. What are the 2 parts of water? Hydrogen and oxygen. All right, so we're going to split it into H2 plus O2. H2 plus O2. Okay, so our first little nugget of information. How can you tell this is a chemical reaction simply by what I have written? Okay. Is it different from how it began? Yes, completely and totally different. Okay. The second piece of information, let's talk about our states of matter. At room temperature, right now in this room, what state of matter is water normally in? Liquid, very good. So do me a favor. Right behind water, in parentheses, write a little letter L. Now, I do it in cursive because it's easier to see it. Because if you just do like the straight line, it looks like an I. Yes, sir. Hold that thought. So my next question is, let's look at the other side. At room temperature, what state of matter does hydrogen like to be in? Well, it's like to be a gas. Okay? And in room temperature, what state of matter does oxygen like to be? Likes to be a gas. So my original question to you was, how can we know that a chemical reaction occurred with our eyeballs? We see it in a chemical formula, but how would I know by visual representation, one of the 5 signs, what would it be? Which one of the 5 would you see? Very good. It is going to be bubbles. Think about this. We asked this question yesterday. What is a bubble? It's a gas trapped in a liquid. So think about it. We've got liquid water, and what are we producing in that liquid? 2 gas molecules. So what would we be producing? We would be producing bubbles. We would be producing bubbles. That's how you can tell with your eyes that a chemical reaction has occurred. The next piece of information. One of the things we talked about yesterday was a word called diatomics. What does diatomic stand for? 2 atoms. I introduced to you to one of them yesterday. Who was that one? Oxygen. How many diatomics were there? 7. Now you know another. Who is also a diatomic? Hydrogen. Very good. And again, the way you know it's a diatomic is because it has this little bitty 2 back here, which tells you it's a diatomic. And again, the definition of a very basic sense of a diatomic is it would rather be with its twin than by itself. Okay? And that's why we have H2 versus O2. Does that make sense? All right, the next topic I want to talk about, and this is reaching back to 8th grade, and a lot of you hated this in 8th grade, but you know what? We're going to make you love it here. Is that reaction balanced? Okay. Well, let me ask you this. What does it mean to be, quote, balanced? Very good. You have the same thing on both sides. So let's think about that. So let's start with right here. How many hydrogens do I have on my left? 2. How many do I have over here? Well, that's good. How many oxygens? And then how many oxygens? Is that a problem? Yes. Here's my question. This is a dumb question, but I have to ask it. To balance my oxygens, am I allowed to come in and put a 2 right there? Does that completely and totally change that chemical? Yes, okay, because remember the definition of a chemical is a definite composition. If you put that 2 in there, what does this now become? Very good, hydrogen peroxide. So that's illegal. You can't do that. So where do you put the numbers to balance a chemical equation? In front, and we call those things what? Coefficients. Does that make sense? Okay. So if I need to balance this oxygen with that one, what do I put in front of the water to balance it? A 2. Very good. So I'm going to come in and I'm going to put a 2 right here. Now here's the problem. In math class, there's a specific property that tells us to what you do on the outside, it applies to everything within. What property is that? The distributive property. Okay. So we do definitely have our 2 oxygens, but did we also change our hydrogens? Now how many hydrogens do we have on the left? Now we've got 4. Did that cause a problem for us? How can I fix that problem on the other side? So add a 2 in front of H2. Now it is balanced. Does that make sense? I assure you, if you didn't learn it in 8th grade, you're definitely going to learn it here. Okay? Good. I'm glad to hear that. All right. Next question I want to ask you guys. This is the question where all the wheels start falling off. But just follow along with me. And it's a simple concept. If I start with 2 waters, listen to how I'm asking this. If I start with 2 waters, how many, this is a number, how many H2s would I get? If I start with 2 waters, how many H2s will I get? 2. Does that make sense? If I start with 2 waters, how many O2s will I get? 1. Where am I getting my numbers from? Okay. So let me ask you this question. This is important. If I start with 100 waters, how many H2s am I going to get? 100 H2s. 100. If I have 100 waters, how many O2s will I get? 50. It's called a ratio. It's a 2 to 2 to 1 ratio. So if I start with 1,000 waters, how many H2s will I have? 1,000. And how many hydrogens? 500. So you will always have half as many oxygens as hydrogens. Would you agree with that statement? It's all based off of what? That big word in orange? The coefficients. And we're going to come back to how these ratios relate to each other. Know how I throw stuff at you all along? So you've seen it. Do me a favor. At the very bottom of, actually I'm going to write it so you can see it. This is called the mole to mole ratio. I apologize about how I had to cram that in there. It's called the mole to mole ratio. I'm not going to say another word about what it means. Just know that where does it come from? What did I do? What thing? I know. I do that a lot. And there's a reason, because guess what? When I come back to it in a few weeks, you'll be like, oh yeah, I've heard of that before. It's not brand new. Okay? So mole to mole ratio comes from the coefficients. All right. So let's look at the picture. Now the picture should make a little bit more sense. I know it's kind of a bad picture. It's hard for you guys to see on yours. But down here at the very bottom, can you see this like red and black wire? Those are those like jumper cable, those alligator clips. That's going to a battery. What's the battery for? Very good. That's giving us our electricity. And inside this tube, there's a metal rod. Why do we need metal? To conduct electricity. So what's happening is we're going to take this electricity, we're going to run it up into these tubes of water. And what is that water going to do? It's going to bubble up. Fantastic. And it's going to produce hydrogen versus oxygen. Now here's one last little thing that we can connect back to what we just talked about. Look at both of those two circles that I have blue circles around. Do you have more hydrogen in the circle than you do oxygen? Approximately how much more? Twice as much. Now again, it's not perfect, not near as perfect, but it is. It should be 2 times as much. There's one other thing I want to talk about. We're going to get to this later as well. Are the sizes different? Could someone tell me why hydrogen is a lot smaller than oxygen? Okay. If you look at hydrogen, how many protons does hydrogen have? 1. Oxygen has how many? 8. Does 1 take up as much space as 8? No, not near as much. Okay, so that's why they're a little bit bigger. All right, we're going to skip that. We're going to go into this. One of the most important things about chemistry is the energy change. Because if you take away energy, you take away life. You cannot have energy. Excuse me, you cannot have life if you do not have energy. So energy is always involved. Always, 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 always involved in anything. And this specifically says when a physical or chemical change occurs. Okay, energy can be in various forms of heat versus light. And again, we've talked about this. Energy only can be used in 2 ways. Can you create it or destroy it? You can only do 2 things. You can either absorb it or release it. That's it. Those are the only 2 things you can do with energy. You can either absorb the energy or release it. And again, it is never created or destroyed. Now, the very next slide, what does it say on y'all's packet? Thermochemistry basics. We're going to do thermochemistry after the test on Monday. So we're going to skip this last little part, and I'm going to come back to it. It's at the very back of your packet, so we're just going to kind of skip through this, and we're going to move on to the next topic. But just know we're going to get really, really deep into thermochemistry and talk about debate and talk about how energy is related. All right, so moving on to section 2, classification of matter. I can't stress to you how important that this picture is, even though it kind of looks weird. You don't want to spend a whole lot of time looking at it. It is important that we understand what matter is and how we classify it. Okay, because it can be classified into 4 things. Okay, it can be classified into homogeneous mixtures, heterogeneous mixtures, compounds, and elements. But being able to figure out what it is an important part of being able to determine its classification. So starting at the very top, we've got matter. So what's the very first question you need to ask yourself about matter? Can it be separated? Okay. Can it be separated? If it can be separated, then what do we call it? Make sure. Do me a favor. Come over here and underneath can it be separated, write the word physically, please. This is a weird question, and I know this is I'm going to get a lot of different answers on this. Can you separate gravel? It's a pain in the butt to do it, but is it possible? Yes. Okay. Are some things easier to separate than others? Absolutely. Okay. But physically, it can be done, and that's kind of what it means. So, if it can be separated physically, regardless of how hard it would take to do it, okay? If I take salt and pepper and I mix it together, could you eventually separate all the pieces back? That would take forever, but yes, it is possible. Okay? And so that's kind of what I want you to see, is that physically it can be done regardless of the time and effort that it would take. If it can be, it's called a mixture. Okay? It's called a mixture. Another word that we can use, and I want you to write this up here, is called a solution. S-O-L-N. Solution. That's another one of my shorthands that you guys are going to have to remember. Solution. S-O-L-N. Okay? So then if it's a solution or a mixture, you have to ask yourself another question. What's that question? Is the composition uniform? What does it mean to be uniform? Does it look the same? Okay? Is it identical throughout? Okay, up there, that the faucet head on the sink. Does that entire piece of metal look identical on the faucet head on the front counter? Okay, it looks the same. Is that one type of element that makes up that stainless steel? Now, a stainless steel is steel anywhere up there. It's still an element. No. So how do you make steel? Very good. It's a combination of things. So would you agree that stainless steel is a mixture? Could I separate all the different metals that are in that thing? I could, and I have to melt it down and be able to figure out how to separate it. It's a difficult process, but it is possible. But my question to you is the composition uniform? Does it look the same? Yes. So it would be called homogeneous. Now, you already know homogeneous is, the prefix homo means the same. So something like air. Now, air is a weird word because when we think of air, we call it oxygen. But right now in this room, is it just oxygen floating around? There's a lot of different gases floating around. So is it a mixture? Could you separate those gases? You can. It'd be hard, but you could do it. But does it look the same? It looks the same because you can't even see it. So that's why air is homogeneous. Sugar in water. Okay. If I have a glass of sugar water and salt water, what's the only way you can tell the difference? To taste it. Okay. It looks the exact same. Okay. And then finally, stainless steel, which is what we talked about. So what if the composition is not uniform? Granite, which you guys know what granite means. Okay, it's those countertops. Wood, look up here on the front counter. Okay, it's all the same stuff. It can be separated, but it doesn't look the same. And then blood. And blood is the weird one. And I always get the question, why is blood? Because if you cut yourself and blood pours out, does all the blood look the same? What it's referring to here is if you take blood and you spin it, what happens to it? It separates, right? It separates into its different entities. Real quick, kind of a throwback to the last chapter. What property separates them into different density? Very good. Which one goes to the top? The specific, like the least dense is what I was kind of looking for there. Sorry. Okay. The red blood cells sit on the bottom. The white blood cells are in the middle, and then the plasma sitting on top. Okay. So the other side. What happens if we cannot physically separate it? Can you physically take salt and separate it? No, okay, you can't. Or sugar, you can't do that. So we've got to do it chemically. So it can be decomposed by ordinary chemical means. So can you take a water molecule and break it into its parts just naturally? You need electricity, right? Okay, so those are some things we would need chemically to do it. Okay, so if you can break it down, it's compounds. If you can't break it down, it's elements, which is everything on the periodic table. All right, so let's look at, this is the exact same picture. It's just kind of flipped over, and it shows you a little bit more perspective of what's going on here. Okay? All right, so the classification of matter. This is everything we talked about in words. A mixture is a blend of two or more kinds of matter, which, and here's the important part. Okay, first of all, two or more kinds, which retains its own identity. Okay? They are also called solutions. And I'm going to add one more word here. Does anyone know what steel and brass are called. Because it's a solution of metals. Starts with an A. Alloys, very good. So, a quote, a SOLN of metals is an alloy. Okay? A solution of metals, which basically means they take all these metals, they melt them down till they're in the liquid state, and they just pour them together. Okay? Why would they do that? It would make it stronger. Okay? Does it change its heat intensity? Does it change its electrical intensity? All of those things make it stronger. What is the difference between 14 karat gold and 24 karat gold? All right, 24 karat gold is pure gold. Everything that's in that substance is literally gold atoms. There's nothing else in it. Okay? But 14 karat gold is subsidized with nickel and zinc, which makes it stronger. So when you go buy jewelry, most jewelry is in which form? 14 karat. There's two reasons it's 14 karat. Number one, what's probably the most reason you're going to buy 14 over 24? It's cheaper. The second reason, and this sounds crazy, but real gold is very soft. Like if you hit it with a hammer, it will shatter. It will crack. Okay, so you would not want that expensive of something on your finger, and you hit it and you crack it or you scratch it. That's not a good thing. So that's why most things that we use are in 14 karat, because it's a lot stronger and it's not nearly as expensive. Okay, so homogeneous mixtures means they are uniform, such as saltwater solution. Heterogeneous mixtures are not uniform, such as clay water. You can definitely tell the difference between the water and the clay particles. Okay, again, prime example of kind of what's going on here. The one thing that I do want to point out in this picture is notice in this picture how the sugar molecules, and I want you to write this somewhere around this particular picture, are mixed throughout. Okay? They are mixed throughout. And most of the time, if you have this other stuff, if you mix it kind of like this, it will eventually settle. Okay? It's not all, but most of the time that stuff is going to settle out because of what property? Density. Very good. Okay? Just a little solution humor. We're going to get way more in depth in this picture a little bit later on, but I'm showing it to you now, so when you see it later, you'll remember it. So I just love hanging out with you, chloride. Hee, sodium. Oh, no. Is that water? What? Where? I'll never forget you. Okay. What's happening here? Very good. Hydrolysis is happening. Okay. What happened to the sodium chloride compound? They got separated. Who separated? Water. Okay. This is going to sound ridiculous, but it's my way of getting you to understand something. Water is y'all know what that word, second word is? It's a piranha. It is. You sure? Look it up. If I've misspelled it, I'll take my claim. It may be one R, but I think it's two. It may be two N's. Well, let's try that again. Spell it for me. Okay, I got you. That makes sense. So let's write that down. My apologies, Jordan. You were right. Okay. So water is a piranha. What do piranhas do? They destroy everything in their path. Now, we can get into the simplistic terms of that water is a piranha, but what Jackson said is important, and this is the chemistry term of it, is called hydration forces. And again, this is the depth that I think is important for us to go. What does hydro or hydration mean? Water. Forces are strengths of attractions. So simply what this means is, if the hydration forces are stronger than that ionic crystal or that molecular compound, and it can tear it apart, then it will dissolve. Does that make sense? That's exactly right. That's why it's called the universal solvent. Most of the time, water is strong enough to tear stuff apart. There are some things that it's not strong enough. I know this is going to blow your mind, but if you take a piece of copper and you throw it into some water, does it dissolve? You may not think it does, but it does a little bit. The reason why is because you can't see it falling off atom by atom. But if you take salt and pour it in water and you stir it, does it separate it? Yes, because you can definitely see it dissolve. But with copper, it's more of an over time kind of thing. It's slower because the metal bond is stronger than the hydration forces to a degree, and eventually it will tear it apart. Okay. There is something else about this drawing here at the very end that's very important, and it is correct, and we'll talk about how that works a little later on. That's exactly right. We'll talk about why or how the water is facing those ions in a certain position. Okay, and I'm telling you, it is very, very, very important. Okay, so again, the whole purpose of showing this is how do we create solutions? Because when we mix them with something, and you said it very well, Joseph, a solvent, when we put it in there, it has to break it apart. That's what does the dissolving. Okay, so physical chemical changes. What's the difference? We've already talked about this. So a physical change of state, physical appearance, composition, or substance does not change. An example of freezing or melting. So do me a favor, out beside this, and I keep saying this for a reason. The state of matter. If the state of matter changes, it's still the same stuff. It just looks different. Yes, sir. It's a physical change. Okay? I agree with you on that. And that's one of the things you have to be able to differentiate between what's occurring versus what you see. Okay? All right. Chemical reaction, substance to composition changes, such as combustion, such as rusting. Now, we've talked about rusting. What's the chemistry name for rusting? Oxidation. And then what does decomposition mean? To break down. Okay, so let's look at this. The little picture at the bottom shows nitric acid in a penny. And if you drop nitric acid in the penny, what are most pennies made up of? Copper. Okay, copper and zinc nowadays. It used to be pure copper, but in the more recent years, copper has gotten so expensive, so they've had to subsidize it with more and more different metals that are cheaper. But what's going to happen is that nitric acid is going to eat that copper and that zinc off of the penny, so that matter of fact, it only eats the copper, so the zinc is what's going to be left in there. Okay. It dissolves the penny. It dissolves the penny. It is illegal to destroy money. Yes, you are right. Okay. All right. So separation techniques. These are the three things that I want to talk about as far as being able to physically separate the components. So sorting by color or sorting by magnetism, gold and iron filing. So we're going to talk about each one of these specifically. So filtration, distillation, and chromatography. All right, so what is filtration? Duh. That's not really hard, right? You guys have seen filtration your entire life, especially if you drink coffee and you make it every morning, then you do filtering every single day. So what we're trying to do is we're trying to get whatever that solid is floating around out of that liquid. The interesting part is, notice the difference here. What is the color inside of that flask? It's yellow. When you pour it through, what is the leftover color? So what is causing the color in the flask? Whatever that solid is. So if you want to come in here and you can write the word solid right here. Okay, and I know that's orange over yellow, but that is the solid that's going to be trapped into that substance. Okay? The next thing, distillation. Okay? This is boiling off one or more components of homogeneous mixtures. Okay, so here's somewhere around this page is we are using different. When I write BP, do y'all know what I mean by that? Boiling points. If you want to write the whole thing, different boiling points to separate compounds. Okay? Using different boiling points to separate compounds. We're actually going to do one of these labs towards the very end of the year. And we're going to do it with fingernail polish remover. Okay? Ladies, what is in fingernail polish remover that makes it smell? Acetone. Most of the product in fingernail polish remover is water. What we're going to do is we're going to remove the acetone by distillation, because acetone's boiling point is lower than water. So what that means is when we begin to heat it to a certain temperature, the acetone will begin to boil, and what will the water do? Stay there. It's not going to do anything. Now again, what is boiling? A liquid to a gas. Now here's the crazy part. How do we then get that gas back? This is what distillation does. Is what we do is we trap it in the top. Okay? Well, when the gas gets up to the top and it can't go anywhere, what process do you think occurs right there? Fantastic. This is where condensation occurs. Now, what is condensation? What happens in condensation? Gas to a liquid. So what happens is it turns back into a liquid, and guess what these little water droplets do? They go down and they slide down this tube, and they end up in our resultant flask. So that's what we do. We boil it out, we let it condensate, and then it travels down that tube, and it just drips, and we are going to be able to collect the remnant, whatever we're trying to get out. So in this particular example, we have salt water. So when they heat this flask up, what's the first thing that's going to leave, the salt or the water? The water. Is the water's boiling point less than salt? Yes. So when all that water boils off, you are going to have what left over in the original container? Just salt. And all of the water should be over here in your resultant flask. Does that make sense? That's what distillation is. This is how they make moonshine. This is how they make alcohols really strong. Okay? They do is they take a diluted version of it, they boil the alcohol off, and what they have is pure grain alcohol. This is what they do to make moonshine. Okay? In a very complex, and then they take the alcohol and they add sugar and flavoring and all that other stuff to it to make it whatever they want it to be. Okay? Any questions? Go ahead. As far as there's something called Mohs scale of hardness. It is not on that periodic table, but you can look it up to determine which metals are harder than others. The what? I would say no, but I could be wrong. I don't think it has anything to do with it. So the higher the number, the harder the metal is not true. It's not true. Okay. Because, I mean, if you think about iron, it's less than copper, nickel, and zinc, and even silver and gold, but it's harder on Mohs scale than, I don't know much about platinum. I know it's really expensive. Platinum is really expensive. Okay? All right, so the last way to separate stuff is by chromatography. So here's what chromatography is. Do y'all know those, and I always misstate it. Well, actually, let's just make it simple. This right here is a Sharpie. It's just a dot of Sharpie. Yep. Okay. So, in art class, what is black? All the colors. Okay. And this is why it gets really confusing in science. Because in science, what is black? It's the absence of light. Okay, it's the absence of light. We're going to talk about that in the next few chapters. Then what is white light? All the colors of the light. Now, when I say colors, what is your rainbow of colors? What's that acronym? Roy G. Biv. Now, I'm gonna go ahead and hurt your feelings, but it is no longer Roy G. Biv. It's Roy G. Biv. They've removed the I. Indigo is apparently no longer a color on the spectrum. So it's Roy G. Biv now. So, but this is art. We're dealing with colors. So here's what we're trying to do. You've already told me that black is the presence of all colors. But what we can do is we can take a solvent, okay, a solvent. And in this particular case, it is going to be alcohol, okay, like isopropyl or rubbing or something like that. It can even be ethyl alcohol or ethanol. And what's going to happen is that's just a little bitty tiny piece of filter paper, just like a piece of coffee filter that's a little bit thicker. And what happens when you stick that filter paper down in that water? What's going to happen, AJ? What's going to happen? Like completely away. What's going to happen when this alcohol hits this filter paper? It's going to run it up, okay? It's just naturally going to tend to pull itself up the paper. Well, will the alcohol travel through that black Sharpie dot? Yes. Well, obviously, according to this picture, what happens to that dot? It separates the colors. Okay? Now, there's a chemistry reason behind why it separates the colors. Okay? It doesn't just magically just separate them. Because if you look over here, do you agree that there is obviously a range and a differentiation of all the colors? It separates it into its specific colors. The reason why is due to this word right here. Polarity. Okay? Now you've heard this, you may have heard this phrase before, is that like dissolves like. You ever heard that? Like dissolves like. Now, I don't like that because I think it's too generic. It's not friendly. The way I say it is polar dissolves polar. So what that means is literally they make a connection. They hold each other's hands. Okay? So what I'm telling you is that this alcohol is polar. And since the colors ran with the polar alcohol, what does that tell you about the colors? They are polar. Because it's kind of a side note. Are pigments made up of molecules? Yes. Everything is made up of molecules, right? So there is some sort of chemical interaction there. So because the colors are polar and the alcohol is polar, it's going to pull it up. It's going to run with it. But here's the question. Why do the colors separate into different intervals? Why does purple only go so far? And then you see the yellow, and then you see the green, and then you see the blue. Why are they separated into different intervals? Since they're different, okay, you told me that colors are molecules. Is each color a different molecule? So is each color a different polarity? Yes. Okay, so are some stronger than others? Yes. Well, let me give you this visual. If I walked outside to your vehicle and tied a fishing line to it, and I pulled at a certain distance, and then I pulled, it was like a twine rope, and then I did a steel cable. Which one would pull it farther? Steel cable. Why? It's stronger. Which one went the farthest? So what does that tell you about its polarity strength? It's the strongest. So here's what I want you to write beside blue. Somehow in this, how do I want to write this? Let me say it out loud, and you guys help me the best way to say this. The farther it goes, the more polar the molecule. Is that about the best way to say it? All right, well, so let's go with that. So, the farther it goes, now when I say it, what do I mean by it? And again, I probably should have said color here. The farther the color goes, the more, and I'm going to say polar, the compound. And again, you already told me that colors are made of different compounds. Yes, sir. I think that just has to do with pigment differences personally. Just because your eyes pick it up a little bit differently. This is a chemical, yes, it's a physical chemical separation. Okay? We are. We are. We're gonna, but you got to learn about it first. Okay. When we get to the polarity chapter, how much time we got left? All right, we'll stop.